Matthias, welcome to Computing Education Things.
Hi Daniel, nice to be here.
Yeah, so we could spend hours talking about Matthias' teaching and service in the computing education field, but this podcast focuses more on computing education science practices than interviews. So this is a teaching episode, and today we're diving into the PyTamaro project, which provides an interesting way to learn programming through graphics. And I think, Matthias, that approaching graphics is a good starting point here because, at least for me, it's an unusual way to learn programming, right? Normally, we hear about graphical interfaces, or if you are learning Python, right? These graphical libraries, or if you are learning R, maybe you hear this term as graphical analysis, right? So I'd love to hear from you about graphics and using this PyTamaro library can be an alternative domain for learning programming.
Yeah, I'd be happy to talk about that a little bit. By the way, on the picture you see on the screen, you see this lake that's on Monte Tamaro, so the Tamaro mountain, and that's why it's called Pytamaro. It's for Python, so it's really nothing, not a separate language, it's Python programming. And the graphics library is called Pytamaro. It's a beautiful mountain. If somebody once comes here to southern Switzerland, you have to go up there. Uh, Let me just say one thing. This is not really my own work. I have a group here and have a lot of really nice PhD students. And the PyTamaro project is primarily Luca Chiodini, you see highlighted here, as contribution for his PhD. So if you're interested to learn more about it, also talk to Luca because he's an amazing person. Very interesting. So, you said you learn to program in different ways and maybe not necessarily with graphics first. One of the questions we had is how do you actually start programming? What are the kind of exercises as a student you would do when you first program? And some of the answers we usually get when we talk to teachers is, yeah, you need to compute something with numbers, right? Like the greatest common divisors, Fibonacci, factorial, prime numbers, and square root, and stuff like that. And that is actually, all of those examples come from a book for learning to program, which has been used at MIT to teach the intro programming course for a long time. If you use that in general, then often you get, by the way, they're all in chapter one, all those examples. Uh, you often get this kind of response from students because not everybody is really excited about math and numbers and such. And so when we did the Pythamaro project, we thought, how could we do exercises for students that are more engaging and more attractive? And you could look at it in these two dimensions. On one way, you want to teach programming. You don't just want to play around. The other one, you want to have something that draws people in and they can't stop programming. And the ones that I just showed, they're maybe on this side. They are conceptually deep. You learn something kind of algorithmically, computationally, but many students just do not find them so attractive. Now, you can also ask not teachers and not college professors, but ChatGPT, how should we teach programming? Suggest some exercises. And if you ask, you will get different answers every time, but usually it's something of this. The first three are what I just mentioned. And the fifth plus palindrome, even and odd, they're not mentioned, but I would place them more on the bottom left corner because they're not only not very attractive, but I don't think you learn that much. Yeah. So you might get this reaction with the students. And if you do something like even and odd, which often is in a Python programming course, maybe also in schools, is one of the first programs because it's relatively simple, or teachers may feel it's trivial. If you look at this from a programming perspective, from a programming language concepts perspective, there's a lot of stuff. Like you may have string literals, variables, you have assignments, You have function calls like input to get your number, but it's actually not a number, it's a string that you have to first convert or parse into a number. And then when you print something and you want to print a number and the string, you do the plus. And the plus is not addition, but it's string concatenation, which may be weird for novice programmers. You use numeric literals, that's perfectly fine, they know that. But also you have some arithmetic operators like this percentage sign. That's not actually percentage, but it's modulo, which they may not be familiar with. You have ideas like conditions, equality. What does it mean for two things to be the same? Selection, if statements. In Python, the indentation that plays a role. That's all complexities that you need to talk about when you teach programming. If you want to then print the result, you need to convert things into a string. So you have a number, you convert to a string. You have to output it, so you call the print function. When you input, the input function in Python actually blocks the program. So the program otherwise just walks forward, and there it stops, which is very strange in a way. So this whole thing, it's just like a few lines of code, but this mixes a lot of concepts. And if students are supposed to fully understand what's going on, you can't just say, yeah, this is the very first program I'm showing you. So
Yeah.
I would say this thing is not even, it's not very attractive. It's not conceptually very deep from the algorithmic perspective. Is it even or odd? It's also not really simple as a very first program. So that was
Yeah.
kind of
Too many terms, right?
the starting point.
So
Yeah, exactly.
I think I'm thinking how I learned programming. I learned programming with C, so that was my first language, and all of these terminology and concepts that you are talking about, I learned them first as a theory, right, and then with practice. But yeah, so studying all of these different syntaxes and everything for a newbie like me was very hard at the beginning. So I
Yeah.
think you are going to tell us about how to make this more entertaining, more fun, but at the same time having all of the relevant syntaxes there and all of the relevant concepts there, right?
Yes, exactly. You got it exactly. You hit the nail on the head. Yeah, so we're trying to make it attractive so students like to do it, but we want them to really understand. And one way to make it attractive would be, for example, let's teach them programming with robots. And I had this episode. I once was at the Tech Science Center in San Jose in California. And they have this beautiful exhibit where you build your own robot and you can plug together those bricks. Some of those three-dimensional blocks are actuators, some are sensors, some are logical blocks. And so by plugging those together, you're programming. And it's kind of engaging. You're programming a real robot that's driving around. It's fun. But in the same exhibit, in the same activity, they also had another station. Like they had a station with those blocks, and they had a station with decorations. So you had things like glasses you can put on the robot, a hat, a nose, even a fish you can hang around the neck of the robot. Guess where most of the kids were? Almost all kids were in the station with the decorations. Very few kids were in the station where you take the blocks and you actually program the robot. So you can make things attractive, but if it's only attractive on the surface with the decoration, you have fun, but you don't learn that much. Right? So that's one of the problems. There's another problem. I'm sure people who teach programming or have been teaching programming for a while, they may do projects. It may be a capstone project at the end of a bachelor. It may be a project at the end of a programming course. And often the projects are on teams. And so you have 2, 3 students that may write a game because games are fun, so they're attractive. And if you look at those teams, very often you have one student who is the graphics designer. So that's the person who draws beautiful graphics that make the kind of surface of the game and spends most of their programming, in quotes, in Photoshop. And the software engineer students, they are going to write the logic of the game, the algorithms of the game. That doesn't really work that well either. So if you look at this kind of let's do game programming to make it fun, you may end up in this spot here where you have a lot of attractiveness, but you don't learn that much. And so that is kind of leading us to where you would like to be in this two-dimensional space. We would like to have a lot of conceptual depth, but also something that's very attractive. And obviously, I don't know how you are actually getting to that extreme point in the spectrum. But maybe we can go a little bit lower, kind of in that direction. And that's what we've been trying with the PyTamaro effort. So the key idea is let's do graphics. Let's allow students to build cool graphics for games or for whatever they need the graphics, but you cannot draw them in Photoshop. You cannot find them on the internet. You have to program your graphics. So program the graphics. That's essentially the motto of PyTamaro. So the
Yeah, and
students
let me
build
add
it.
here, Matthias, because I was, trying a few activities on the PyTamaro website that we can dig into later. But it's interesting how you approach learning there, right? I encourage everyone to try out using the links in the description. But for example, I found a watermelon exercise there.
Mhm.
So I first have to try to define the ellipse, and then I do the same thing, but you introduce me a new variable and ask about the difference between the first example and the second example.
Mhm.
And if you follow that path, I think it's clearer to me why it's important to name things in Python, for example, and you are doing it in the fun way, as you said, right? Which make it more interesting, I think, in my opinion.
Yeah, yeah. You bring up an important point. This whole naming thing, that we name things properly, that is really, I think, essential. And often the naming that is used in introductory programming may not be the most useful somehow. So we actually build up from small components, and then students name the bigger things, and they give them names that are meaningful. And because we have graphics, usually when you look at a piece of a graphic, you can say, well, this is the key, or this is the hat, or this is the head, or so. So you can identify a thing in a graphic and give it a name. And in our programming approach, those names are going to be the variable names for those graphics. So we really start from the very basics. You mentioned the watermelon example. I can show that afterwards quickly. We really start from like just that. We have a bunch of primitive graphics, and everything else, like a rectangle and an ellipse, and everything else is composed from those primitive graphics. That's kind of the way we do it. You build it from the bottom up yourself, and then you can build all your game assets that you use in your game in that way, and you learn while designing the graphics. And you also practice key skills that you would have, that you would say you need to know when programming or computational thinking, like how to decompose a problem, how to recognize a pattern, and also how to do abstraction. I think abstraction is at the core of programming. And what you said with the names, you usually give a name to an abstraction. You say, this is the hat, or this is the function that can make a pencil of any color, or something like that. So those three things are at the core of PyTamaro. And maybe the most central one is this decomposition. And here is one of the activities that you may have seen already on the website. So students may want to, or have to in our curricula, compose this kind of graphic. It's a graphic of a simple flat design pencil. And if you ask them, you say, how would you build this? How would you compose this? How would you decompose or break it down into pieces? You may say at the end, there is a pink eraser, then there is this silvery ring, and then there is the body of the pencil that's kind of yellow, and you have the point and stuff like that. Or if you ask them to draw a, what's it called? The Swiss German name is Himugüegali, but
Yeah,
the
it
English one
works.
is a ladybug or something like that, right? So if you say, how is this built? You start with this one picture, this one graphic, and ask the students to decompose it. And you say, yeah, a head, a body, two wings. Or a little bird, how is it built? Well, it has the eye and has a wing, has a body and a beak. Or this sign here, which a teacher did in the Czech Republic I recently was visiting a middle school teacher who uses PyTamaro. And he asked the students to go on the street and find traffic signs, take a picture of a traffic sign and come back. They had no clue why they were doing this. And then he said, do you know why you're doing this? We're going to program those things. We're going to write the Python code that draws this graphic. So you could break this down as well. So that's decomposition. The second thing is another computational thinking thing, a skill, which is pattern recognition. So if you look at this graphic, which is another activity from our website, a ghost, like you would have it in the Pac-Man game. If you say, could you see a pattern here, something that repeats? You would see that the bottom of this ghost has all those triangles. And you see it's repetitive. So there's a triangle, and then you have many copies of that. So there's identical clones, you could say. And if you're thinking about writing a program that draws a figure like that, an initial student might write 6 lines that draw 6 triangles. Do a triangle, do a triangle, do a triangle. And that's a great start for teaching loops. Say, well, you don't want to write this 6 times. That's code duplication. It's bad for software engineering. And then you do that. But it's more difficult. Sometimes you have patterns that repeat, but they're slightly different. Like here you have the traffic cone, a European one, not American, so it's kind of triangular. And you could say there's a repetitive pattern here, like this what is it called? A trapezoid of one of those orange or white rings. This repeats, but every instance of this is slightly different. It gets wider and the color changes. Yeah. So that's the second one. And the last one is abstraction. And when you have a graphic like this one, this is basically showing a battery indicator like you would see it on your phone or something like that. You can ask the students, what is in common for those 4 graphics? And they would say, well, maybe it shows the battery indicator. Okay, what is different between those? What are the similarities? What are the differences? And the differences would be, well, it's charged a lot or it's not that much charged. And this is a great start. We're talking about graphics, and now we can switch to programming, and we can say, could you create a function, define a function that produces this battery indicator? What would be a good name for the function? And now we write names, which you mentioned. Well, it's not F, it's probably battery indicator. So why not define a function named battery indicator? And then if you look at the differences, this would be the level. Like, is it full? Is it discharged? This probably some number. Maybe it's a floating point number, 0 to 1 or something like that. And what does the function give back? It gives back a graphic. And you can do many such things. Like here we have a few rounded rectangles. What are the changes here? You have the width, height, and corner radius and the color that changes. So you can define a function with those parameters. Or here, actually, there are many more possibilities, but I can go out online on the website and to show that.
And I think, but this helps a lot to understand PyTamaro, I think, because, you know, as you said, right, we cannot only rely on the fun side, right, or the decoration side of the programming, because we don't learn, right? But at the same time, I think it's very important to have a visual understanding of the problem. And you are showing us like that we can be more familiar with these images and then do the problem decomposition better, right? Because if not, it's very difficult to, you know, sit in front of your desktop with, empty page in front of you or an IDE, right? And program this, right? It's easier to have this image in mind.
Yeah. It's a concrete problem, and it's something that you can see the picture, you can see the graphic, and you can see the parts, right? It's not like you don't need any technical skills or programming skills. You can show this to anybody and say, what are the pieces here? And so that really helps to practice this problem decomposition. Of course, it's about graphics, and later on, you want to transfer this skill to other domains. You want to decompose something where you need to do a graph algorithm or something else. But initially, it's very tangible. It's very like concrete. Yeah.
All right. So as I mentioned in the beginning, right? This is a teaching episode. That means we can now discuss, right? How to integrate PyTamaro into teaching practices, because I think, as you mentioned, the fundamental programming concepts are the same. So you mentioned, Fibonacci and those problems that I also did in the past, but I want to understand better how to, integrate, right? How PyTamaro can help computer science educators teach those concepts in a way that is more entertaining and fun, and also it's useful for the students.
Yeah,
So
yeah,
maybe, I don't know, if you want to switch to the website, we are 20 minutes from
yeah,
now on the
yeah.
episode. So maybe you can, we should jump to the website and you can show us some examples.
Yes. So, with respect to integration, we have a website that you see here, but as I showed in the slide before, we also have a Python library. So if you don't want to program in the browser, you do not need to do that. You can just download the library and then you use your normal Python IDE and you can create those graphics outside of this web platform. But the web platform I have open here, it has more than the library. You can run the programs in the browser, but what's key is we have a lot of activities there. So we created those activities when we did a teacher training for preparing teachers who are not computer science teachers in high school to teach computer science in high school. So we wanted to have a lot of example activities for them that they could do in their course where they have to teach programming. So that's the main reason why we have this platform. And a lot of teachers now are using the library. Some teachers are using the platform, and some teachers even create contents for the platform. So we have a kind of collaboration with a bunch of teachers who work on this platform. They contribute through GitHub. So we have our thing all on GitHub, and the contributions in the form of activities is done by working on developing something like a Jupyter notebook or so, and then pushing the changes to GitHub, triggering a redeployment of our web platform. So teachers are really, every day, they're pushing new content on there. So if you want to program, maybe I'll show you here a couple of activities. So you have lots of graphics that you could pick if you're a teacher. If you want to teach a certain concept, you can filter here and say, well, I want to see stuff that has to do with loops. And then you see graphics that are somewhat repetitive. I mean, you have this idea of patterns that repeat. So that would be something you do with loops. So you can really kind of pick here which concepts you aim at. Let me use this example here with the Swiss flag because it's simple. We can do
Yeah.
that in a short amount of time. So, sorry, if you go to one activity, you end up on one of those pages, and it looks a little bit like a Jupyter notebook. So you have explanations, and then you have code cells that you can edit and you can run. So let me reset this quickly because I had done something before. Okay, so now our page has lots of tasks and we're going to solve those tasks. The very first says we need to create a red square. So the background of this Swiss flag, we know we can do a rectangle and it says 320 by 320 and it's red. If I run this code cell, all I get is it tells me it's been executed. But we didn't do any output. We didn't say print, or for us, we don't actually print, but we show the graphic. So if you call show graphic, it shows. Otherwise, you just did something in computation without showing it. So the next step is we need to compute the cross, the white cross, which consists of two arms, which are rectangles. So we rectangle 280 and white. And then here we have another rectangle, the vertical one. So rectangle 80, 200 and white. And then we need to compose those two to make a cross. And to compose it, we have a function called overlay, where you put one in front of the other. So you say overlay of the horizontal arm and the vertical arm. And this should give us a cross. So I can run the cell and there's no error. I can't see the thing. It's a little bit
So, w-
suspense in this specific activity. Every activity is different. So here we said, let's first build everything and then we show it in the end. In other places, you want to show the output all the time.
yeah, so
So
you didn't
last,
mention, but you are calling, well, you are here invoking the PyTamaro library, right? So,
yes,
so,
exactly.
so here, there, can you explain in 1 minute what we can find there in this library?
Yes. Let me go quickly to the slides because I have that in here. So the library is as small as possible, really small. So we have only those primitives. You can draw rectangles, triangles, ellipses, circular sectors to make like a pizza slice or a Pac-Man, and a text. And then we have another set. So that's 5 functions you need to explain to students. It's not like 100 or something like that. And they're relatively simple and clear. And then we have functions to compose things. So if you have 2 graphics, we can overlay them in front of each other, like I did for the cross. If we have 2 graphics, we can put one above the other graphic. Like here for the Ukrainian flag, you have a blue rectangle above a yellow rectangle. Or here is the Ticino, my state here, coat of arms, where you can put one half beside the other half. So those are 3 functions with which you can compose a graphic and get a new graphic. That's essentially the way the library works. So you decompose something, some big graphic like a Pac-Man game. You write the code to produce all the little pieces, and you call functions like overlay to put the little pieces together so that you have in the end the complete graphic. And that's kind of what I did here. So I created a rectangle, which is one of the primitives, and then I called overlay to create the cross out of the two rectangles. And we see here that I'm importing from the PyTamaro library. I say which functions I need. So I'm not using the print function or the input function or the max function or len function or range function that people usually use in Python. But overlay, rotate, white it's just a constant for a color. And I'm almost done with the flag. And I have a cross and I have the background that's red. So I need to put the cross in front of the background by overlaying it. So overlay the cross on top of the background. If I run this, again, it will just tell me, blah, I'm done. And the very last thing I do is I output this. So I don't print it. I could say print, so I can say print here, print 1. I run it, and it's going to print 1, but that's not very exciting. I prefer saying show graphic flag, and I should see my Swiss flag. Now, we see it, but you may notice it doesn't look exactly right. So we actually made those arms of the white cross too thick. So I can go back up and I can try to improve things. So we have it here. We say rectangle 280. So let me say it's 260. And I go back down and I rerun the program. I fixed one of the arms. It's now 60 tall, but I forgot to fix the second arm.
Yeah,
And
the
this actually
vertical
is
one. Yeah.
something, yeah, we try to work towards to tell the students, if you have something like that you build 2 graphics, those 2 arms of a cross, and they're actually the same, it's just one is rotated, then don't copy the code, write it once. So if you look here, we say we create a rectangle 200 by 60 white, and then we create a rectangle, now we could fix it, 60 by 200 white. Can't we just say that the vertical arm is the same as the horizontal, but it's rotated? And yeah, we just say rotate by 90 degrees the horizontal arm. So we only have one place where we say how wide an arm is and how long an arm is. And that's it. If I do it wrong, I have one point in my code to fix it. So that's one kind of pedagogical thing, which is a little bit of software engineering that we push in the very beginning of the curriculum. So students write cleaner code. So let me
Yeah.
see whether I actually made a mistake. No, it looks
Mm.
fine.
Yeah, yeah,
Okay.
exactly. And then finally, you show us like what you learn, right? And it's a brief description for those who are listening here on the screen. Yeah, basically you
Yeah.
explain everything you got from this example.
Exactly. We usually have that's something that's content that's contributed by the author of this activity page, but we kind of have this tradition of always writing at the end what you learned. But we also have something in the platform. So if somebody creates what we call a sequence of activities, not one activity, but a whole sequence, we call this a curriculum. So you can go and you find quite a few curricula on the web platform. Here is one that we usually point people to when they start. It's called the welcome curriculum. And a curriculum is a little bit like, I don't know, Duolingo, where you have like this trail you need to go through to learn things one after the other. But sometimes you have choice. You can do one activity or the other activity. If you like rugby, you go this way. If you like watermelons, you go the other way. It covers the same concepts. You learn the same thing, but in a slightly different context. And so you walk through those activities in order to learn certain skills. There can also
Yeah,
be optional activities sometimes.
maybe we can go to one of these examples because I think I want to show listeners and everybody the features you created. I think the not showing the solution first is very interesting
Mhm.
feature. So can you go to one of these examples and
So we
and
can
see
go
how
to
is
the,
the interaction?
yeah. So, well, here, I mean, normally we show, in most cases, we show them the graphic that they're supposed to create. And then we ask them how they will create the graphic. Let me reset this activity again so we don't see it.
Yeah,
So
that way. Yeah.
one of the features we have, and that's actually something the original idea we stole from the people who did how to design programs, the group around Sri Ram Krishnamurthy, Matthias Hauswirth, and friends. They have online books, kind of, and they have this component that says "Do now," but students just skip that component. They just read on. And so we said we would like to have a "Do now" that tells students don't read on. Think
Mm.
right now.
Yeah.
This is the point in time you should think about this. So we basically blur all the rest of the page, and you have to confirm that you did it. I mean, there's no check, right? You can do nothing, but it stops you at least, and you say, oh, okay. And we have some of those components where you have to fill in an answer before you can move on, before it unblurs. But I think it's enough just to have this button that triggers you. It's like, oh, I should not move forward. I should
Yeah.
actually think right now. And then you go on and you do the cells step by step and you go through. Now, one of the things with those competencies, like what you actually learned, you see here on my left, I have this sidebar with a lot of pills, and this activity here teaches me certain things. And this activity is one in this bigger curriculum, so a whole sequence, something you would spend, I don't know, a month or 2 months on in a course in schools or so. So you can look at the curriculum, and that curriculum is the sequence of activities. And we have a description of the curriculum that may be more for the teachers, where you can see all the activities and all the competencies that you acquire in there. So you could say that's like learning objectives or learning goals. You see the first activity where it's focusing just on performing output, which is kind of something you need to learn. And then it's about importing names, using names, literals, arithmetic, types, and all those kind of programming language concepts. And when you complete an activity in this curriculum, you basically gain that skill, that competency. So over time in your sidebar, you will see your competencies and the numbers are going to go up because you have done many activities that has to do with using names or with defining a function or things like that. So it serves a little bit as a I don't know, you could say achievements, but it's not a star, a gold star or points. It actually is really tied to this is the concept I want you to understand, and the number shows how many activities of that concept did you practice.
Awesome, Matthias. So yeah, I think that's all, folks. Thank you so much for your time, Matthias. And yeah, and see you in the next episode of Computing Education Things. Thank you, Matthias.
Thanks a lot for having me, and I'm looking forward to seeing other episodes in the future.